All right, let's dive right into one of the most mind-bending scientific proposals I have ever come across. We're talking about a serious, testable plan to actually search for an echo from before the Big Bang. It's the kind of question that, it feels like it belongs in philosophy, not a physics lab. But what if there was a way to actually check, to listen for a message that might just be older than time itself? Well, that's exactly what this is all about. So here's our game plan. We'll start with the basic idea, this echo from before time. Then we're going to look at the very specific signature they're hunting for. We'll see how they plan to listen from two completely different places, why the test is so brilliantly designed to be proven wrong, and finally, what it all means if they actually hear something. Okay, so first up, an echo before time? I know, it sounds like total sci-fi, but some cutting-edge physics models like loop quantum cosmology, they actually leave the door open for structure and information to have existed before what we even call time. This isn't just a thought experiment, though. It's about a concrete physical test. And this is where it gets really wild. The proposal connects three things you'd never ever think to put in the same sentence. The idea is that a single ancient signal could be picked up at the same time in the vibrations of charged dust out in space, in the structure of certain light waves, and get this, even in the slow electrical hum of a forest right here on Earth. So, what is this echo, really? What are they actually looking for? Well, the whole thing hinges on finding a kind of secret signature, a way to hear something profound that's been hiding in plain sight, buried in the noise of the cosmos and our own world. The key is what they call a dual resonance signature. Okay, imagine you get a secret message. To know it's legit, you have to receive it in two different languages at the exact same time, and they both have to match perfectly. That's the idea. They're not just looking for a blip, they're looking for a very specific predicted link between two different signals that are vibrating together almost like they're saying the same thing. So the proposal is tuning into three channels. First, you've got terahertz light. That's just a part of the light spectrum. Second, dust acoustic waves, which is literally the sound that travels through charged dust in space. And third, the real curveball, the tiny little shifts in electricity in a forest, which apparently can act like a giant, super-sensitive biological antenna. The theory is that a huge solar event, like a coronal mass ejection, could act as a massive amplifier, making this hidden signal suddenly detectable across all three channels at once. So how on earth do you find a hidden structure in all that noise? You use this really fascinating mathematical tool called Betty spectroscopy. Now, the simplest way to picture it is like this. You take a simple signal, like a wave, and you use a clever trick to fold it into a really complex, multi-dimensional shape, kind of like a weird donut. Then you count the number of holes in that shape. The theory predicts that if something meaningful happens, the shape itself and the number of holes will change in a specific, measurable way. It's a method for finding structure that normal analysis would just completely miss. This brings us to the actual plan. See, the genius here isn't just the wild idea, it's the incredibly clever and practical way they're going to test it, using this two-track approach. They're running two independent investigations at the same time. Track A is about looking into the past. It means digging through old data from legendary missions like Cassini and Voyager, looking for this exact signal signature during solar storms that have already happened. Track B, on the other hand, is about listening now. It means setting up a live sensor network in a forest paired with a terahertz detector to try and catch a signal in real time during the next big solar flare. The beauty here is that these two tracks are totally independent. A success in either one would be a huge deal. And now for what might be the most crucial part of any great scientific idea, making sure it's a test that's built to fail. The real strength of this proposal isn't just how bold it is, but how clearly it defines failure. It's designed to be proven wrong. Any signal they might find has to clear three incredibly high hurdles. First, the signals from the different channels have to be statistically linked, and with a very high certainty. Second, the pattern of that link, that dual resonance, has to be stable, not just some random fluke. And third, this is the real killer test. The signal in one channel has to actually be able to predict the signal in the other. If it fails on any of these, the whole hypothesis gets thrown out. And as you can see here, these are clear, hard pass-fail gates for both the space track and the Earth track. There's no wiggle room. For them to claim anything, the data has to pass every single gate for that track. One fail, and it's back to the drawing board. This is what good, responsible science looks like when you're pushing the absolute limits of what we know. And the authors, they tackle the biggest potential criticism head on. They make it absolutely clear. This isn't some kind of quantum mysticism. Every single measurement is classical and physical. They're just using the fancy math of topology as a really powerful tool to describe the shape of the data they're measuring. No magic here, just math and measurement. Okay, so let's wrap this up by asking that huge question. What if we actually hear something? What are the real-world implications if this crazy-sounding experiment succeeds? Or, for that matter, if it fails?
Well, the critical thing to understand is that this experiment is a win no matter what happens. A positive result? I mean, that would be world-changing, the first actual evidence for information existing before our universe, connecting astrophysics and biology in a way no one ever imagined. But a negative result is also a huge success. It cleanly and cheaply closes off a speculative idea, which is essential for science to move forward. And maybe best of all, there's a practical spin-off. The tools they're building could create a whole new kind of early warning system for dangerous solar storms, which is a massive benefit all on its own.
So we've gone from a mind-bending theory all the way to a concrete, practical experiment. It's just a perfect example of how science pushes boundaries. So I'll just leave you with this thought. This whole project is about more than just one experiment. It's really about a new way of listening. And it makes you wonder, if the universe has been speaking a kind of hidden language this whole time, are we finally, maybe, just starting to build the right dictionary to understand what it's been saying?